Hello everybody, and welcome to exercise 5 on page 64 of the workbook. And in this example, they're asking us to reverse the order of integration to calculate the value of an iterated integral. Now before we dive into this, why would we want to do that? Why reverse the order of integration? Okay, well, if you look at this integral, if we wanted to do the integral as it's stated right now, the first thing that we would have to do is to integrate e to the x to the fourth with respect to x. The problem is that e to the x to the fourth, it's one of those functions that doesn't have an elementary antiderivative, so it's not possible to do that integral and come up with a closed form antiderivative in the form that it's in. In other words, we can't find the exact value of this integral without finding a different way to do this. That's the purpose for reversing the order. We're hoping that by doing that, it'll get it into a form where we can do the integral exactly. Okay, well, before we can reverse the order, we need to have an idea of what our region of integration looks like, which means we need to draw a picture. Okay, and that means kind of analyzing the curves that are involved in our limits of integration. So let's start with the inner integral. We're going from x equals the cube root of y to x equals 2. Okay, and picturing x equals 2 is not bad. That's just a vertical line. X equals the cube root of y, I don't know what that looks like immediately, but if we take that equation and solve it for y, it's going to be easier to figure out what curve we're looking at. So let's cube both sides. And we notice that that curve is equivalent to y equals x cubed. That's a graph that you might already know what it looks like, or you could punch it into your graphing calculator and take a quick look. Okay, so since those are our bounding curves, let's go ahead and sketch the region. Okay, so y equals x cubed is a curve that kind of looks like this in the first quadrant, and x equals 2 is just a vertical line. Okay, so those two curves there and there. Okay, I'm going to label those. So x equals the cube root of y on the left, and then x equals 2 on the right. Okay, and one thing that might be of interest to us is, what is this point of intersection up here? Could we figure out what that is? Okay, well, we can see that that point is on x equals 2, and if you take x equals 2 and substitute it in to the equation over here to the left, you can take that equation and solve it for y, and what you're going to end up with is a y value of 8. Okay, so 2, 8 is actually the crossing point of those two curves. Okay, and just to confirm that we've got the right region here, let's go back to our integral for a minute. Okay, so if you focus on the inner integral, we're going from cube root of y to 2 on the left and the right, so that would take us in this direction. And then we're going from 0 to 8 in the y direction. Notice that that's also correct. Y equals 0 is down here, and y equals 8 is up at the top. Okay, so we do have the right region, and we're ready to roll as far as reversing the order of integration here. All right, so let's get rid of just a few of our markings here. Okay, so we'd like to take that integral that we started with and reverse the order of integration. Okay, it just means that we're going to be integrating the same function, but we're going to go in the y direction first and then in the x direction. Okay, and the challenge with this type of an integral is always in figuring out your limits. Okay, so integrating in the y direction first means that we need to know what y is equal to on the bottom and the top of our region. Okay, we've said a couple of times before that for that inner integral, your limits of integration should be curves. So what is the equation of the curve on the bottom? Well, it's a flat horizontal line, so we're going to get y equals 0 everywhere on the bottom. And then, okay, if we draw our typical rectangle, what's the equation of the curve on the top? What is y equal to there? Well, we already know that the equation of the curve is x equals the cube root of y. We just need to solve that equation for y. And in fact, we already did that over here. when we cube both sides. We discovered that y is equal to x cubed. Okay, so we can see, putting it together, we're going from the curve y equals 0 on the bottom to the curve y equals x cubed on the top. That means that our integrals are going to be, or our limits of integration are going to be 0 to x cubed. Okay. And now we're done with the y direction, so we are going to shine a light down the y-axis. Okay, and ask yourself, what would the shadow of this region look like? Okay, so if you shine the light straight down the y-axis, the shadow is just going to be the part that's underneath this region from here to here. And what range of x values are we talking about? Well, x is equal to 0 here, and x matches the x-coordinate here of 2 on the other side. Okay, so our limits of integration are just 0 to 2 for the x's. All right, so the harder work is done now. We've reversed the order of integration. Now the question is, can we do the integral? Well, let's see. So our inner integral, we are integrating with respect to y. Kind of interesting, because if we integrate with respect to y, we're treating e to the x to the fourth like a big constant. So if you take the antiderivative of a constant with respect to y, you're just going to get y times that constant. Okay, so I'll write it as y e to the x to the fourth. And we're evaluating that between y equals x cubed and y equals 0. Okay, actually I'm going to go to the next line. I don't want this to get too cramped. Okay, so if we plug in x cubed and 0 for y, we're going to get x cubed e to the x to the fourth on the top. And then if we plug in y equals 0, we're just going to get minus 0 on the bottom. So we're really just taking the integral from 0 to 2 of x cubed e to the x to the fourth dx. Okay, we need to do that integral. Okay, and you might recognize this from either Calculus 1 or Calculus 2 as a u substitution type of an integral. Okay, we can let u be x to the fourth, this part here, and that means that du is 4x cubed dx, and if we solve for dx, we're going to get du over 4x cubed equals dx. Okay, so if we go back and substitute all of that in, okay, we're going from x equals 0 to x equals 2. X cubed e to the u. Okay, dx becomes du over 4x cubed. And notice that we get the cancellation that we want. That's the sign that we probably chose a good u. Okay, and we've got an over 4 in the bottom, which we'll pull out as a constant. And we're really integrating then just e to the u du. Okay, but what happens when you integrate e to the u? You get, it's the nicest antiderivative in the whole world. You just get e to the u back again. Okay, evaluated between our limits. Oh, and I just noticed I really should have written x equals 2 up there. Okay, last step would be to go ahead and substitute that u back in. U was equal to x to the fourth, and now we're evaluating between 2 and 0, and so let's see what we end up with here. So we'll get 1/4 e to the 2 to the fourth, which is 16 for our upper limit, minus 1/4 e to the 0, and e to the 0 is 1, so we're going to get a final answer of 1/4 e to the 16 minus 1/4.